Map is a routine that takes two ranges of numbers and one value in one of the ranges, and it gives you the corresponding value in the other range. Now, that may sound kind of dry to you, but in fact, we do this sort of thing all the time. We just don't always recognize that we're doing it with numbers. If you've ever done color selection in Photoshop, then you've been doing exactly this. You start with a color in a given color range, and you turn it into a different color in a different color range. When we use Photoshop's interface, of course, we're just talking about colors, but under the hood, Photoshop is using numbers, and it's using something very much like map to make this happen. Here's another everyday example. If you've ever tried to use a slide projector to project a slide, you've done map. You know that this is a tricky task. You have to move the slide projector in and out, you have to tilt it up and down, you have to move it left and right, you have to rotate it. It's a lot of work to get the picture on the screen to look really good and be in the right place. This is another example of map. What you're doing is you're taking the colors that are on the little slide that you're projecting, and you're turning them into colors on the big screen. On a smaller scale, if you're using a data tablet, you're already using map. If you're using a tablet that has a built-in display like this person is, or if you're using a touch screen, then generally you're making a mark right where you're touching. If you're using a more traditional tablet, then you have to make some kind of a correspondence between where the pen is touching the tablet and where the mark appears on the screen. Often, we make it one-to-one. We say that the entire surface of the tablet gets mapped or referred to the entire display surface of the screen. So if I make a mark, say, in the upper left of the tablet, it shows up in the upper left of the screen. But you don't have to do it this way. You can say, for example, just this region of the tablet corresponds to the entire display. And so now if you move your pen around inside this smaller, darker yellow box, you're still moving over the entire surface of the display. Or you can say on the display, I only want to be referring to this box. So now the dark yellow box. So now when your pen moves around inside the dark yellow box, the cursor makes corresponding motions in the dark red box. This is another example of mapping. Let's see map in action. On the left, we have a man wearing a green shirt, and we want to turn it into a purple shirt. So what would be great is if we had a little routine, and what the routine took in was the range of colors on the left underneath his shirt, the range from dark green to light green, and the range dark purple to light purple, and a particular pixel somewhere on his shirt, let's say this one. It takes in the two color ranges and that pixel, and it gives us back the color that we want to replace that pixel with. So we hand it any green color anywhere on his shirt, and we get back the corresponding purple color. This would be great. Well, this is exactly what map is all about. So let's strip this idea down to its very simplest form, where we're just manipulating some numbers, and then you'll see that writing code to do this sort of thing with colors is going to be very straightforward for you to write. Here's our basic setup. The yellow square at the top is our data tablet. The blue rectangle underneath is our display screen. Now, just to give these things some numbers, let's say that the data tablet is 100 pixels wide, and the display is 185 pixels wide. If we draw some sort of a curly shape on the data tablet, it turns into a similar curly shape on the display, but it's wider. Let's ignore the y value for now and just think about the x. So the x coordinate of every pixel in the yellow box has a corresponding x coordinate in the blue box. To prevent the slide from getting too cluttered, I'm going to get rid of the curves, but remember, that's our basic motivation. What we want to do is to stretch the yellow box. We want the left-hand side of the yellow box to go to the left-hand side of the blue box, and the right side of the yellow box to go to the right side of the blue box. The way we do that is by taking the x coordinate inside the yellow box and turning it into a new x coordinate in the blue box. So what are the relationships? Well, the left-hand side of the yellow box is 0, and the left-hand side of the blue box is 0. The right-hand side of the yellow box is 100, and the right-hand side of the blue box is 185. So here are the basic relationships. The left-hand side goes to the left-hand side, so 0 goes to 0, and the right-hand side goes to the right-hand side. So 100 goes to 185. If we can make that happen for our x values, everything works perfectly. The yellow box gets stretched. Remember from our earlier picture of the data tablet, I said sometimes we only want to use a piece of the input area. So let's go ahead and do that. Let's say we only want to use this dark orange part of the input. And we want just the dark orange part to get stretched into the whole of the blue thing. Okay, so we have to move the arrows in because now we're stretching the orange box, not the big yellow one. And we have to change the numbers up top because the width of that box no longer goes from 0 to 100. So let's get rid of those numbers, 0 to 100, and replace them with what they really are. Let's say the left-hand side of the orange box is at 10. So let's put that in our rule at the bottom. Now we're saying that an x value of 10 goes to 0. Looking back at the picture at the top, the right-hand side of the orange box, let's say it's at 75. Then the rule at the very bottom says 75 goes to 185. Now if I touch anywhere in the orange box, it will get stretched to the full width of the blue box. So let's write these two rules side by side horizontally. Let's follow an actual point. So let's look up at the orange box at the top. Suppose I touch my pen down here. Let's call that x. Now, of course, it's two-dimensional, it's x, y, but we're ignoring y for now. We're just looking at the horizontal part. What we want is the corresponding value in the blue box. Let's call this x2. x2 is our output. We're going to take the four numbers that are in the rules at the bottom and the value of x, and out comes x2. Let me show you how to write that. I'm going to clear everything off so we can keep it very simple. Remember that our dark orange box is 10 at the left and 75 at the right. So let's put those numbers down at the bottom of the screen. The light blue box is 0 at the left and 185 at the right. So let's put those numbers down at the bottom of the screen. Look now at the dark orange box at the top. That's our data tablet. Suppose that I touch my pen down at this point. Well, it has coordinates x, y, but for right now we're ignoring the y, so all we have is the x value. Let's bring that down. And what we want out of this whole process is the spot in the blue box, this spot right here, which I'll call x2. We want to know that value, so let's bring that down. How do we find x2, the value on the left, from the stuff on the right? All we have to do is to call map with those numbers in that order, just like this. Put commas between them, wrap them up in parentheses, stick a map at the beginning and a semicolon at the end, and we are set. So this is map, and it might take you a while to really appreciate just how useful this is. You're going to find yourself using this all the time, particularly when you use the mouse. So why does this have the weird name mapping? It turns out that comes to us from mathematics. This is a common kind of thing that we do in math, and in that field, it's been called mapping for a very long time. So when people adapted it for use in computer programs, well, they just kept the name. Let's return to our example of color shifting and see how map helps us do this. Remember, we had a guy who was wearing a green shirt and we wanted to turn him into a guy wearing a purple shirt. Think of the gradient underneath the green shirt as the input range, and the color gradient under the purple shirt as the output range. The value we're mapping is the pixel that I've surrounded in red. So let's say that this has a fairly bright green color. Well, that's going to be our value of x. The output is the corresponding location of x in the purple range, and that's x2. You often see map written in a way like this. Now there's a lot of arguments here, no question. There are 5 of them, and that makes it kind of confusing and hard to remember. But let's walk through this because it's not so bad. The first one is v, that's the value. The value we start with belongs to a certain input range. And I'm marking that here as S1, E1 for start 1, end 1, the starting and ending values of the first range. Those are followed by S2 and E2, the starting and ending values of the second range. What comes back is the value V2, the number between S2 and E2 that is in that range in the same place that V is between S1 and E1. Everything here is a float or an int. If you want to map colors, you would call map 3 times, computing new values for either red, green, and blue, or hue, saturation, and value. Although it might seem a little obscure, map is so incredibly useful that it's definitely worth playing around a little bit. Mapping numbers in this way may be a new kind of idea to you, and it may still seem a little bit foreign, but it's really just about patterns. It's just about making patterns with numbers. I really recommend playing with this a little bit. Just mess around with it and try drawing different graphics and experiment with it. Once you get the hang of map, it is going to become an indispensable part of your everyday toolbox.